Okay, we're going to work 4.47 at this point in time. It's a fun problem. It reads 38.5 milliliters of a lead 2 nitrate solution reacts with excess sodium iodide solution to yield 0.628 grams of a precipitate. And we want to know what is the molarity of the lead 2 plus ion in this original solution. So at first, you may be really confused by this problem. There's a lot of ideas kind of thrown together here in an unusual way, okay? But if you're ever faced with a reasonably difficult problem like this one, maybe one you haven't seen before, try to take an inventory of what you know, build a picture of what you think is going on, and then see if you can reason your way through the problem, okay? And this is something that you can get better at with practice, okay? And I think that this type of problem is something that, you really need to develop this skill for, because otherwise you might just kind of be lost, and that makes a little bit of sense, okay? So let's take a look at it. So it seems like there's a reaction that's going on here with this lead nitrate and excess sodium iodide. Okay, so I'm keying on that. I think, okay, well, if there's a reaction to make some kind of precipitate, it sounds like a precipitation reaction. I kind of know what a precipitation reaction is all about. I make a solid. Maybe I could write a chemical equation, a balanced chemical equation for what's going to happen here. Okay, so I got lead, which is Pb. It's lead 2, so it's 2 plus, and then nitrate, NO3. I guess if I want to balance that at the onset, I do that, right? This is all aqueous phase chemistry, as precipitation reactions always are. So I'm going to have a solution of that, and I'm going to combine it with sodium iodide. And sodium iodide is what? Na is sodium, and iodide is I. It's a +1 and a -1, also aqueous phase. Okay, so I'm told I have excess of that. Maybe that's important. We'll see. But right now I'm just thinking about the reaction. So if it's a precipitate, okay, maybe it's a precipitation reaction. Well, what can happen? Well, I guess I can get my ions switching partners, so maybe I make NaNO3, but all nitrates are soluble. Also, sodium salts are soluble, so that's not going to be a precipitate. But what's the other possibility? Well, I guess lead 2 plus. Oh, I've got lead and iodide. Oh, maybe that's an insoluble precipitate. All right, that makes sense, because a lot of iodides are soluble until they're paired up with heavy metals like lead. So actually this lead iodide is a really pretty yellow colored compound that would form if this experiment was carried out. And just to kind of keep track of things, it looks like I make 0.628 grams of that eventually, okay? Now, as I'm looking at this, I might want to kind of condense this precipitation reaction down just to the nuts and bolts, that net ionic equation of what's going on here, okay? And I think if I end up doing that, I could write Pb 2 plus aqueous plus 2 I minus aqueous yields Pb I2 solid, right? That's my net ionic equation for the chemistry that's occurring. So this makes a little bit more sense now, okay? So I got some of this lead nitrate solution. I'm going to mix it with the sodium iodide. That's my source of the I minus, right? And I'm told that there's excess. So now that I've identified the problem, I'm going to start thinking more stoichiometrically or more quantitatively. And I note that word excess. That tells me I've got plenty of that around. I'm not going to run out of that first, which means I'm probably going to run out of this when I'm going to start talking quantitatively about how much of that I made. Now, I was told in the problem that I made 0.628 grams of the precipitate. Seems like that precipitate must be the solid lead iodide, and I've made 0.628 grams of it. So you can kind of see what I'm doing now. I've taken the information that I've been given, thought about it a little bit, and I'm starting to make an inventory of what I made, what I have, to make sense of all this, okay? How I can reason my way through it. Now, I know I made, as a result of this reaction, 0.628 grams. That was my yield, right? It's the yield of the reaction. And if I'm running this reaction under conditions of excess I minus, it stands to reason then that what's limiting how much of that I can make is how much of this I had to begin with, right? Once I run out of this, I can't make any more lead iodide. So it seems like the amount that I've made is somehow tied to the amount of this that I originally had. So let's kind of expand upon this a little bit further then. Maybe I could take my 0.628 grams of this material and I could convert it to moles. And I'm going to do that by dividing by 461.01 grams per mole. The reason why I'm dividing by that number, that's the molar mass of my lead iodide solid. It has a pretty high, hefty molar mass, right? Because lead and iodine both are pretty heavy atoms on a molar basis, okay? So if I do that, it turns out that this quantity of 0.628 grams corresponds to 0.001362 moles. So all I've done is I've converted this 0.628 grams into moles of that substance, right? That's how many moles were produced in the reaction. Now, why did I do that? Well, grams is a mass. It's not a counting unit in terms of the way that we write our chemical reactions. In a reaction, we say we take one of these, two of these, make one of these, right? One of those, two of those, one of those, right? It's very stoichiometric, very ratioing of compounds to make different things. I can't do that with masses, but I can do it with moles. So if I had this many moles of that, that's what I produced. Doesn't it stand to reason then that since it's a 1-to-1 molar ratio, that I must have consumed 0.001362 moles of lead to make that much of the lead iodide? It's a 1-to-1 molar ratio, so that has to be true. So look at what I've got. I've now backtracked my way through the problem, understood that I made a precipitate, figured out how many moles of that precipitate I made, and now I figured out how much lead must have been used to make that precipitate. Now, in the conditions of my precipitation reaction, I was told I had excess of this, which means that the amount of this I make is limited by this. Once I run out of this, I can't make any more, right? So I've used all of this up. That's how many moles I must have used of my lead 2 plus ion. Now this is very valuable information, right? Because I'm trying to find the molarity of that solution that I used. Where did this lead come from? Well, it came from this 38.5 milliliters of the lead nitrate solution that I originally had and I used in the reaction. So what I know now is that my number of moles of lead that was present in that solution is equal to 0.001362 moles. And because I'm dealing with solution phase chemistry here, I know that my number of moles of a solute is equal to the molarity times the volume in liters. So as a result, I can write my number of moles of my lead, and that has to equal to the molarity of the lead times the volume in liters. Now my volume in liters, what is that? Well, I was given that in the problem kind of indirectly here, because I was told that I used 38.5 milliliters, right? So if I convert that to liters by dividing by 1,000, moving the decimal places 3 spots, it's 0.0385 liters of solution. That times my molarity has to equal this number of moles, right? And that makes sense. I have 38.5 milliliters of my solution. There's a certain molarity. The number of moles that were used to make this stuff has to come from that solution. So this is kind of just like a conservation of mass type of thing. But of course the beautiful thing about this now is that I've got one equation with one unknown. I can rearrange and solve for the molarity of my solution as 0.035337 moles per liter. That has to be the molarity of the silver ion, the lead ion in that original solution to make this work out. So this is a nice problem. Not only does it involve general knowledge of what's going on in the solution, precipitation, chemistry, being able to predict products of that correctly, but also a little bit of stoichiometry in the solution phase. So hopefully you're able to master this.